So this lecture is on Fourier transforms, 2.3. We have the Fourier series under our belt, and you should see online on the webpage there is new homework. I'm going to make it due Friday again because I feel like, yeah, I mean we've actually covered all the material that we need to cover in order to do all the homework, but yeah, I just feel like I'm going to give you guys till Friday because I don't know if I would have made it extra hard. I think it might take a little longer than you might be able to do by Wednesday. So
Considering it's already Monday.
It's from the textbook. It's mostly Fourier series stuff, but then next week we'll do more transform based stuff. But I thought I would give you guys a little more time on it. So Fourier transforms, we're going to approach it a little bit differently. I often lecture like this, where I go general concept, what are we doing, try to fit it in with the broader class that we're studying, and then I give like the theoretical underpinning of it. Here's the theorem, or here's the law, or here's the definition, or whatever, and then I apply it to something. And there's an example. That's typically how I do my lectures. And I felt like for the Fourier transform, looking at the definition isn't all that insightful. So I thought we would start with the Fourier series, which is something that's a little bit more intuitive, I think, for us, and then work our way, build our way, and show how there's a sort of continuity between it and the Fourier transform. And there's a similarity between it and the Fourier transform. They're very much related. And yeah, so we're going to try to approach it. And then towards the end, I'm going to give you the definition of the Fourier transform. And then we'll talk about applications and whatnot at the end. So it's a little different setup today. I hope it doesn't throw you for a loop. Another different aspect of today is that I'm using, I did the lecture in what's called a Jupyter notebook. Has anybody here used Python before for anything? Okay, nobody yet.
No experience in coding, sorry.
Yeah, well, hopefully you will find that you pick it up easily. Sorry?
A few that have not looked into yet.
Yeah, well, it's a fun language. I would say I like it. I don't love Python. I like Python. I like Ruby a lot better than Python, actually. But that's just me. They're very similar. But I like Mathematica. I'm moving away from Mathematica, though. I know.
What does Ruby do?
What did Ruby do? It's the built-in data structures are really nice. So, yeah. No, actually, Python's more engineering oriented, I guess, data science oriented. I think Python's actually becoming very threatening to the MATLABs of the world, MATLAB, Mathematica, because Python has a lot of data science people and engineering people who have developed really good tools in it that compare to MATLAB, but they're free instead of being very expensive. So yeah, it's a little bit more more difficult to get going, I think, in Python than it is in MATLAB, for instance. But I actually really recommend it. And so I'm actually doing this in the notebook interface for a Python based language called Sage Math, which was actually created up at UW. I don't know the guy, but what's cool about it, if anybody's seen Mathematica before, it's pretty much just like Mathematica notebook. You can type in like text-based cell, put in hyperlinks and all that, and then evaluate it, and it looks like this. Then you type in another cell, and it's a code-based cell, and you can evaluate it, and all of the variables are defined, and then you can reuse them. So just for, because I'm introducing this, I haven't done it before, I will do a quick, instead of Sage Math 1, you can do a Python kernel, which is fine too. So for instance, I could say x equals 5, okay? And then I could say if x, if x is less than 7, then we can say print x. What is going on?
Have you tried, I think it's new Octave?
I haven't tried Octave, but
This is just like diet MATLAB. I don't like it.
I don't know what's going on here. I haven't had this issue.
I guess not.
I think the other, maybe it's because the other kernel's going right now. Maybe it doesn't like that. I just started using this notebook interface. It's pretty new for me. But for instance, if I did it in this notebook, which I think is working, I can just type in the Python, evaluate it. I kind of expected to see x printed. This is a really bad demonstration. X is less than 7, right? Yeah. You don't have to. Let's just see if we can do this. Well, that's probably what's going on here. I can't get even that to work. So, yeah, I'm really not selling this. Maybe I should.
There's a whole bunch of false advertising right now.
Okay.
Don't get your MBA.
Haha. No plans to.
So you feel like you're just looking at hieroglyphics.
Sorry, I didn't mean to.
We've had coding and control. None of them ever taught us any of that. So work on that. Yes, think back. When did anyone ever taught us this? That we would. It's like shift function control. No, the only thing is the basic C class. Did you ever go to high school? Like, have coding? No. My high school just got it like 3 years ago. Honestly, my high school didn't have physics or calculus. Okay, that's sad. That really is sad. I jumped off into an engineering degree with basically no hope.
Sink or swim.
Yeah, like we tried my AP statistics class. Like, can we take calculus instead? And we were like, let's take a vote.
Hey!
7 people. I was like, let's take calculus. Everyone was like, no.
Yes, it did. So It's like, so I was just doing this simple example. If x is less than 7, print hello. Yay, it does that. Print x, it can do that. So, I mean, it's just, whatever. And you can, in the next cell, you can use x again. So,
Change x to 8.
so you could do like x divided by 4, and it comes out as 5/4.
These graphics suck.
In decimal form.
Yeah, I don't remember the, I think it's like
Make Mario.
float. Yeah. Yeah. So, I mean, there's lots of fun stuff. With Python, I mean, you can do essentially most of what you can do in MATLAB. And you can use this notebook environment, which is pretty sweet. So I'm using it. I'm trying to like incorporate more and more of this type of thing into my classes because I really feel like it's valuable for you guys to learn this stuff.
Should I just like download Python and just go Python?
Yeah. Roughly speaking, yes, but you know what? I can try to show you guys or give you guys a little like tutorial page to get your environment set up if you want. I don't have access to a Windows machine to tell you how to do it that way, but it's going to be analogous. Yeah. So for the Mac people, for the Linux people, but Linux people are used to it. Like Linux people are just like, yeah.
Yeah.
Linux is free like a puppy.
Well,
Like it's a lot of work.
Linux onto the laptop, but,
I love that.
now I have to
Say.
hack into that laptop every time.
Okay, so this notebook, so there's like there's all of this upfront stuff that looks kind of scary, but really it's just loading in all these different packages and setting some like formatting preferences for me. So I evaluate that. Here's another cell. Here's another cell where I've got some like LaTeX equations in here, like the delta and all that, so you can get those to render nicely. So yeah, lots of cool stuff like that. But let's walk through it. Let's walk through it on this, and we can play with it as we go and see how much fun we can have. So the source of this lecture, this notebook, is available. So this tells you how to get Jupyter and how to go to SageMath. But if you go to this site, you can download this notebook right there. So for those of you who are interested. We import the packages. Matplotlib is used to make MATLAB-like plots, and NumPy is used for MATLAB-like numerics. Yeah, so let's consider, so now we're going to talk about Fourier transforms. Actually, what we're going to do is we're going to use Fourier series to approach Fourier transforms. So let's consider a periodic function, f, with period t. And then I put in parentheses the monospace font version, the one that I'm using in the variable I'm using in the code, so t there. Each period, the function has a triangular pulse of width delta, which in the code I'm going to call pulse width, and height delta over 2. Okay? So I'm going to, first off, have all of my little controls here. So save figures is something that I set to false because I don't want to save these. But when I'm generating the PDF for the notes for you guys, I had it on true so that I could save it. But for now, I don't want to save the stuff. T equals 20. Whoa.
Oh, so that's pretty good, right?
Start off
low and then it just keeps getting louder.
Yeah, that is intense. So t is a parameter that I'm going to set, and that's the period of this periodic triangular pulse. Okay? So the triangular pulse of a certain width, and we're going to define how frequently this occurs. So period of 20 is what I'm going to set it to for now. The pulse width is the total triangle base width, which I'm setting to 2. F1 is a function, which is the pulse width divided by 2 minus the absolute value of x, which is a triangle that starts off at delta over 2 and it ends at positive delta over 2, and time negative, it's negative delta over 2. And then I'm also going to define a second pulse as well, just for plotting purposes, just to sort of show you. And in order to define the second pulse, I had to just move it over by the period. Okay, omega max is going to be the maximum angular frequency that I want to plot on my line spectrum graphs. So, and then n max is the corresponding harmonic, the maximum harmonic we're gonna plot. Okay. Okay. So first we plot the function f in the time domain. Look at that, editing on the fly. We plot the function f in the time domain. Using the Sage Math piecewise function, due to its Fourier series methods, which we'll use in a moment, we define it and use the matplotlib to plot it. So this is my definition that I'm going to use for the Fourier series method that we'll use later. So a method, those of you who aren't familiar with programming at all, or object-oriented programming, object-oriented programming defines classes of objects. Okay, so objects, like for instance, an array would be a class of an object, and there would be certain methods that would go along with an array. So the object, say x, might be an array with 3 values in it. Well, you might have a method in there for an array that is to sum up the values of the array. So like the array might have the method sum in it. So then you could create an instance of the array x, so x is equal to array of 3 values, and then you could call the method sum on that array, and then it would give you the sum, return the sum. So that's the type of thing. That's what object-oriented programming. That's how it organizes itself. It's similar to, but radically different than in some ways, functional programming, which is you define a function, you hand objects to functions. But anyway, so the piecewise class for Python has this nice method, these nice methods for finding the Fourier series components. So I wanted to use those, that's why I'm using this piecewise definition. We could have rolled our own in this case. In some ways I wish I would have rolled my own in this and not used their built-in function, but anyways, decided to. So, good. So this is the one we're going to use for that, but I'm going to define another one that has 2 periods in it, just for the plot. Okay. Capital N is going to be the number of points to plot. TPP is going to be, so I loaded in NumPy and I'm using this linspace function, which creates a function with, or an array with n values in it. Okay, so 201 values, ranging from negative t over 2, so half the period negative in negative time, to 3t over 2. And I did that range because I wanted to make it look pretty in the plots. That's the only reason why I chose those. And then FPP, so this is like me not knowing a ton of Python syntax, so I was like, I know how to do a for loop in Python, so I'll just use that to evaluate this function at each time step. Probably there's a faster way to do it, but you can always just do a loop like this. So for I in the range from 0 to n, so for integers 0, 1, 2, 3, up to n, append the following value to the FPP array. So I evaluate the function FP, which is this piecewise one for plotting, evaluated at the time value, TPP, and I append it to the FPP array. So I'm building this array up every time around the loop with one more value. So it gets bigger and bigger. And then, if you're familiar at all with MATLAB, this is going to look a lot like MATLAB syntax right here. And the idea is you open up a matplotlib figure 1, you make it the current figure object, then you call these different methods on it. So plot is one, and you give it the time array and then the function array, which you created for every time point. So you have an array of time values, an array of function values, and you can put them corresponding to each other. And then this is just formatting. So I want it to be a blue line with a blue solid line. Okay. And the line width is 2, just the thickness of the line. I want to label the x-axis time. I want to have the limits go from -t/2 to 3t/2. The x-tick values, I'm going to make them look fancy with maths in them, but it would have just put numbers there instead. And the same with the y-tick values. So I made it look all sexy and stuff, but most of this is just formatting. And then this is just saving the figure to this TIKZ format, which goes in nicely to my MATLAB or to my LaTeX that I create the PDFs from. This is, I don't need to, this part is just formatting for the PDFs that you guys got. So nothing really functional there in terms of making this graph. So then I just show it. So I display it here. And look, I've got 2 triangular pulses where they peak at delta over 2. The width of them is delta, right? So 0 to delta over 2, and then 0 to minus delta over 2. So width is delta, height is delta over 2. And then the period is 25 seconds. So this is where the first pulse happens, and this is where the second pulse happens, and on we assume from there. So for delta equals 2 and the period equals 5 seconds, 15 seconds, and 25 seconds, the left-hand column of this figure that we're going to generate shows 2 triangle pulses for each period t. So when we get, oh yeah, you guys, we're going to have to switch over to look at that figure, but la da da. Where are my figures? There it is. Okay, so I did it for different values of period. So pretty much notice that these time axes, I'm zooming out in order to fit both pulses, the first 2 pulses in. So the width of these pulses is staying the same. I'm just zooming out because I'm making the period longer. So 5 seconds in this top one, then 15 seconds, then 25 seconds. So I have to zoom out more and more to get both pulses in because the period's getting longer. So there's more and more time in between these pulses. Okay, so that's what this is showing, and I created all that in here with that. Okay, so Good. Consider the following argument. Just as a Fourier series is a frequency domain representation of a periodic signal, a Fourier transform is a frequency domain representation of an aperiodic signal, which we'll rigorously define the Fourier transform in a moment, but for now we're just going to say, oh, it's a frequency domain representation of an aperiodic signal. So Fourier series, good for periodic signals as a frequency domain representation of them. Fourier transform, good as a representation of aperiodic signals in the frequency domain. The Fourier series components, or also known as the coefficients, of the Fourier series, will have an analog then in the Fourier transform. Recall that they can be computed by integrating, they being the Fourier series components, can be computed by integrating over a period of the signal, right? That's how we computed those ANs and BNs is in the last lecture is we computed the integral over one period, right? We usually went from negative t over 2 to positive t over 2, I think is what we did. So if we increase that period infinitely, the function is effectively aperiodic. So that one period, think about it getting stretched out more and more, kind of like what we're doing here, where we're stretching out that period more and more and more, 25 seconds. Imagine if it was 2,500 seconds, there would be a lot of space between one pulse and the next pulse. And it becomes effectively aperiodic as you stretch that off to infinity, that time interval. Okay? The result within a scaling factor will be the Fourier transform analog of the Fourier series components. Okay? So that's roughly what we're going to be doing, and then we're going to try to approximate that by showing it as it emerges from the Fourier series, as we stretch that out in time more and more. So let us approach this understanding by actually computing the Fourier series components for increasing period. So that's kind of the idea, is we're going to do that, and then we're going to see what it looks like, and then we're going to find, oh, that's just the Fourier transform, is what it's approaching. Okay. Sage Math has nice methods for its piecewise class, Fourier series cosine coefficients, and Fourier series sine coefficients. They compute the Fourier series cosine and sine components an and bn for component n in period t. Now, you guys, we did it by hand last time where we computed the integral by hand. You could also have Mathematica or MATLAB or Sage or SymPy, or any of these things compute integrals for you as well. I decided to use this one because I thought it was convenient. So I'll build that up as follows. The cosine components and the sine components, I'm also going to compute the harmonic amplitude, which remember is the square root of the sum of the squares of an and bn. And I'll compute the angular frequency at each value. So I'm just here. I'm not pre-allocating. I'm just defining that they're empty arrays, and then I'm going to populate those arrays in this for loop. So it's kind of easy, sort of procedural steps here. So I'm just going to go from I to n max. N max was the highest harmonic we were going to go to. Okay, so for each harmonic, I'm going to compute the cosine one. So this is an. I'm just going to use that function and then just slip it right into the f cosine array. Similarly for the f sine array. And then the harmonic amplitude array I'm going to append with a homebrewed formula here, which is a scaled version of the harmonic amplitude. So there's the harmonic amplitude. I guess I should make this a little bigger. It's kind of hard for you all to see. Is that better? It's a little less intimidating when the code's bigger. I feel. So this is saying take the square root of an squared plus bn squared, which is just this, right? And we've scaled it by this scaling factor, which it's not obvious from this point of view, but after you plot it, you see, oh, if I just multiply it by this, then when I change t, then the plot doesn't change. So that's a convenient scaling factor, we call it. So yeah, so we can do that as long as we say that's what we're plotting, right? That's totally fine. So good. Now we're going to do the plot. And the plot of so we want to plot the harmonic amplitudes, which gives us, what do we call that? What do we call the plot of the harmonic amplitudes? So it's what we did for the square wave we computed in the example problem. So it has to do with frequency domain. It's a plot in frequency. We call it the line spectrum, right?
Where we see all the different harmonics in a row.
Exactly. So we see the harmonic. So we see this in the frequency domain. It looks like a function of frequency, but it's only defined at discrete values at all the harmonics. And that's what the harmonic amplitude is the height of each of those peaks, spikes. So good. So once again, we open up a figure object, and this is just to set up the stem plot. So I'm going to plot omega, which is an array of all of my harmonics, versus the harmonic amplitude. So that should give us a stem plot. Stem plots are ones that have a point, and then they connect a line from zero, from the axis, horizontal axis, up to the data point. And line spectra are often plotted with stem plots. It's just a convenient way to plot them. Good. And then we can do the x label, x limits, y ticks again, saving the figure again, blah, blah, blah. And we get this, which I got to zoom out just a hair to get in. Okay. So pretty. So pretty. So what we have is all of our ANs and BNs went into this, like we computed last time. We took the square root of the sum of the squares of them to get CNs, essentially, and then we scaled it, and we plotted them. But we didn't have to compute them by hand this time, which is totally better. And it looks pretty cool. And then if we change our period, say, let's change it, let's go down to like, I don't know, 7, which makes our which makes this look a lot closer, right? Our two pulses are a lot closer together now, so it's a lot less like that that approximation where the period is infinite, right? And we evaluate this plot. We see, oh, well, it kind of looks the same, but sparser, right? So if I up that, so I'll go up, let's see, I'll do 35 because we're just going to be crazy. So this is getting to be a lot more as if they're infinitely far apart. They're just longer ways apart now. We can see the line spectrum is aha! Looking pretty smooth, right? And something's starting to emerge here, definitely a pattern. As we increase that period, as we move each pulse further and further away from each other, we're getting closer and closer to a continuous curve that's shaped definitely like if you connected these dots, right?
Can you put like 5,000?
I could, but we'd probably be here for a while. Yeah, I probably would do it, but so this actually, the computation, my understanding of it is so far is that this actually happens in the web, at least some of it does, and so yeah, there's some connectivity stuff you gotta navigate, but it's pretty good. I mean, it's pretty solid. Also, I think if you pay, you get like server time. I'm just using the free one. But I think if you pay, you get like more server time or something, so it gets faster. I don't know. But I'm cheap.
Man, how much does it cost to get an additional CPU?
No idea. didn't consider it. I was like, free option? Yes, thank you very much. So this just has to do with the nice figure that I show in here, where you can see this line spectrum as we move the pulses further and further apart, how they start to approximate this continuous line. Okay? And so the line spectra shown in the right-hand column of the figure I just showed you. Note that with our chosen scaling, as the period increases, the line spectra reveal a distinct waveform. So let f be the continuous function of angular frequency omega. So f of omega equals delta over 2 times sine squared of omega delta over 4 over omega delta over 4 squared. Where did I come up with this? Well, essentially, I just knew what the Fourier transform of this was. We haven't defined what that is yet. And I just wrote down that Fourier transform. And this function is actually called a, so sine of x over x is called the sinc function. Well, there are a couple definitions of the sinc function, but that's one of them. It's a pretty cool function. Anyways, we're using sinc squared, which is the Fourier transform here. And then there's a scaling factor out front, which is the width of the pulse, over 2. So I'm going to plot it first, and we're gonna look at this, and I'm going to say, wow, that looks a lot like what we were seeing from the Fourier series plot above, right? It's essentially that approximating continuous function that we were approaching with the Fourier series. So consider the plot of f. It's obviously the function emerging from all of the stem plots, from increasing the period of our pulse train. Now we are ready to define the Fourier transform and its inverse, and for that I'm going to skip over to this. So yeah, beautiful, so cool. So here's the definition of the Fourier transform, and it looks quite similar to this is the trigonometric form of the Fourier transform, to the Fourier series definition, the trigonometric form. There's an a and a b in the Fourier transform side. So in the analysis or the transform, you take your original function, y of t, and you plug it in, you multiply it by cosine omega t, which we did before, and instead of summing over a bunch of things, instead of integrating over a period, we integrate over all of time, the whole thing. Over ever. Peter? Is that, what is that? Neverland? Is that, what is that? Is that Hook?
Peter Pan?
Peter Pan? Yeah, the Lost Boys. What is that? What do they call it?
Oh, Mary?
Never, is it called Neverland?
Neverland? Like,
Neverland.
are we talking about Michael Jackson Neverland or?
The Peter Pan, they go to Neverland and
Yeah, go to Neverland. So you integrate over Neverland. I'm working on that.
you integrate over the boundary.
We'll come back to it.
Never and forever.
Yes. So you integrate over all the times. And instead of dividing by 1 over t, you don't divide by 1 over t because t is infinity, and that would make it 0, right? So you can't do that. But you can, so you integrate like this, and that's the a and the b. So they're very, very similar to the Fourier series versions of the integrals. And then the inverse transform, or the synthesis, you construct in a very similar way. Instead of sums over discrete ANs and BNs, you integrate over A of omega and B of omega multiplied by cosines and sines. So that's the sort of analogy there. It's pretty cool, but I'm going to disappoint you by saying we don't usually use this form. This form is mostly fun because it's very much intuitive and close to the Fourier series version. But then we're going to skip over and we're going to look at the complex form. This is the most important one. This one, if you're keeping track at home, this is the one you put the star by. Okay. All right. So the Fourier transform, which in this form we'll actually use the script f to denote taking the Fourier transform of something. Do you guys remember when you took Laplace transforms, how you did script L? This is just like that, except for script f.
Well, yeah, Laplace transforms made no sense.
Yeah.
So,
Well, fortunately, Fourier transforms will make so much more sense.
You said so much more sense. Do I hear like a bit of relativity there?
May have been hedging just a little bit. So, the Fourier transform of y of t, we can denote with this script f of y of t if we wanted, or we could denote it as capital Y of omega. That's another way of denoting it. It means the same thing. So whereas you tend to use lowercase letters for time domain, you typically use uppercase for frequency domain. Then you run into problems with like your variables already being capitalized in the time domain, and then you're like, what, should I make them lowercase in the frequency domain? Should I just write them bigger? Should they be bold? It's confusing.
Find a new like space where it is like super caps.
Yeah, actually the Rowland Wormley textbook for system dynamics uses a little hat for the Fourier transform one. I don't really like that one. I like the caps because that's how I learned it. So that's what it should be. Okay, so that one is analogous to the complex form of the Fourier series. And instead of having the cosines and sines, we use this e to the j omega t in the integral. And you just plop your y of t in there, integrate over all time, and you've got your function of omega, and you're good to go. Alternatively, you could take the inverse Fourier transform, which is the synthesis side. So if you had a spectral representation in the Fourier transform form of y, so y of omega, you take the inverse Fourier transform to get y of t back, which would be this integral. Okay, so we're almost done. So now we have defined the Fourier transform. There are many applications, including solving differential equations and frequency domain representations called spectra of time domain functions. Okay? There is a striking similarity between the Fourier transform and the Laplace transform. Maybe you had equal reactions of joy when you saw the definitions.
I remember learning about Laplace.
Which, you should be acquainted with the Laplace transform from differential equations class. In fact, the Fourier transform is a special case of a Laplace transform with Laplace transform variable s equal to j omega instead of having some real component. So you may recall that in the Laplace transform, s was equal to sigma, a real part, plus j omega, an imaginary part. Now, in the Fourier transform, we said sigma is equal to 0. And that's actually the only mathematical difference between the two. Both transforms convert differential equations to algebraic equations, which can be solved and inversely transformed to find time domain solutions. Okay? So you guys did that with Laplace transforms. You were like, here's a differential equation. Take the Laplace transform of it. Okay, solve algebraically for the output. Inverse Laplace transform to get the output as a function of time. That was what you all did. It was good times. You could do the same thing with the Fourier transform. Now, the Laplace transform is especially important to use when an input function to a differential equation is not absolutely integrable and the Fourier transform is undefined. For example, a step function or a ramp function. So if you wanted to integrate, use the Fourier transform to find the Fourier transform of this function. So 0 and then some constant value, which is really useful in a lot of engineering systems. We do that where there's no input and then we suddenly put in some constant input. You can't do the Fourier transform of this. It's not defined. It's not periodic because it's only this transition only happens once. And yet you can't take the integral because it doesn't converge at infinity. So it sucks. So there's no Fourier transform of it. Yeah, so you're hosed in the Fourier transform. But actually, the Laplace transform was originally developed from this consideration. The Laplace transform was like a generalized Fourier transform. However, the Laplace transform is also preferred for initial value problems due to its convenient way of handling them. So remember that when you take the Laplace transform in the differential equations, the initial condition terms show up in there too? Yeah. That was nice. Fourier transform doesn't have that happen. You can do it in some weird way, but it's not worth it. Laplace is way easier. The two transforms are equally useful for solving steady-state problems. Although the Laplace transform has many advantages for spectral considerations, the Fourier transform is the only game in town. So if you want to get a function of omega, the Fourier transform is the only way to go. Or the Fourier series if it's a periodic function. Okay? A table of Fourier transforms and their properties can be found on the course website in the resources section. And I'll give you guys some practice using that Fourier transform table. It's just like the Laplace transform table.
Yay.
But like with script F's instead of script L's. And there's different stuff in there. So, that is the Fourier transform. You aren't going to be doing any of it on your homework for this week. It's going to be focused on the Fourier series, but next week your homework will include Fourier transforms. So, it's good fun. I'm actually really enjoying this chapter. I hope you guys are too.
Is it weekend after coming?
Yeah.
The quiz is Friday night.
Friday, yeah. I'm going to try to get us the next week back on Wednesday because I know you guys have busy lives and Friday night is not a good night.
I thought it stays on Friday, so I have less stuff on Wednesday.
Well, no. You should open it on Thursday, so that way we have all day Friday to do it, so that we can finish it before we go out on Friday.
I've been down this road before. I've been down this road and it doesn't work very well.
Thursday, not Wednesday.
Yeah, Thursday's like awful.
Like everything. Yeah, well, that is like the worst thing possible.
So you guys like Friday better than Wednesday?